Thank you all for having me here. So what I'd like to do is give a sense of an emerging opportunity, perhaps. And there's some still, the question mark is really intended not as a provoking thing here, but truly the question remains. And so I'll kind of explore this idea of turquoise hydrogen, which the kind of grand theme of that is, can we take the carbon out of natural gas, or even better, bio-derived gases, and sequester that long term and displace materials in doing so, particularly high CO2 intensity materials, a potential double win there. And so that's what I'll talk about. I always like, when I'm in the audience, to kind of know where someone resides, at least intellectually. And so, as Aga said, my group is nanomaterials and aerosol engineering. And what that really means is I study small objects that float around in gases. And typically, I'm interested in high temperature gases. And the kind of tradition of this discipline, and a little bit of my early work, was on soot, right? So one of the things humanity has spent the most time studying is why a candle is orange, so to speak. And that is because the soot is incandescing. And we, humanity, have spent a great deal of time understanding that carbon, the solid carbon that forms in those materials. So that's kind of where this discipline is born out of. Lots of implications for that, everything from contrails and gas turbine engines, which we're interested in. Now, other emerging emission sources, such as brake and tire wear, that are very prescient and might ultimately be a greater source in urban areas than, say, tailpipe emissions as we electrify. So in doing that, we've been really interested in what are the structures of these materials, how do we describe them mathematically, what are their implications for health, climate, radiative forcing, lots of things that deal with structure, surface properties, Maxwell's equations interacting with these materials. And then, as you can imagine, there's lots of ways we'd like to measure these materials, and so my group has been particularly interested in making measurement techniques to understand these emission sources. We've had a number of spinouts from my group over the years where various PhDs and postdocs have taken technologies we developed in the lab and went out, and most of it has been at regulatory emissions. So the idea is that, we, humanity, have decided that, for example, all vehicles sold in Europe, and the UK still, require us to count all of the particles that come out of a tailpipe. But we don't count all the particles, we actually only count the solid particles. And so you might imagine that most particles have some liquid and some solid associated with it. And we, for reasons of robustness in testing, have decided only to count the solid, and therefore you need to remove all the organics, and we use catalysts to remove the organic portion, and so you're left with just solid. So that's kind of one of these items here. A variety of other things where we're making microfluidic devices that can maybe sense the aerosols around us, and then kind of more laboratory grade instruments as well. And so that's kind of measuring the bad things in the world. The other half of the group is trying to make some good things, hopefully. And so one of them is battery materials. Manar, a PhD student of mine who just graduated, spent her whole PhD and several before working on battery materials. So we've done a lot of aerosol synthesis of battery materials. We've got big projects that are spinning up on methane catalysis. Particularly, can we take the methane in the atmosphere and remove it? That would be a big win right now, because actually you don't even need to remove the methane, you just need to convert it to CO2. And you might kind of clutch pearls and say, oh, we're making more CO2. But actually that would be a big win for climate now, because the radiative forcing or the global warming potential of methane is so much worse than that of CO2 that you'd get about 97 to 99% reduction if you converted methane to CO2 now. And then finally, what I'll spend the majority of our time talking about today is actual sustainable carbon synthesis. And the question, that I posed at the top of this is, how sustainable is it, and what could it ultimately do in terms of displacing? So in terms of kind of setting the scale here, what we, humanity, have done for a long time is kind of the dumbest thing one can do with methane, and that is combust it, right? It's kind of the easiest thing. It's what thermodynamics would drive it all towards, which is you turn all of the carbon and the hydrogen into H2O and CO2, and with that, about a ton of methane gives you 50 gigajoules of energy, thermal energy, which then you can use to create work. You're limited by Carnot efficiencies in those cases, so you can't certainly convert all of that energy into useful work, but a good portion of it, depending on how you use it. But then the big problem is, of course, you're generating 2 3/4 tons of CO2 in the process. an alternative approach is you say, we'll take the hydrocarbon, but we'll leave the carbon as solid carbon, and we'll use the hydrogen as an energy source, and we'll leave the carbon solid, and you're going to give up about half the energy, and this is ideally, thermodynamic ideal, in doing so. And so to make that attractive, absent strong regulation to prohibit it, that solid carbon needs to have a functional value that is kind of nominally equivalent of the half of the energy that you gave up. So that's a motivating factor in and of itself. And of course, regulation can play a role in maybe giving other motivations to do this. And so one could do it, of course, with natural gas, but you might also look at other things that are going to be emitted to the atmosphere, or just other sources of methane or other short C species, C1, C2 species. And so everything I'll talk about today we've confirmed with landfill gases and biomass pyrolysis. So you can use other sources of this. It's not so specific to how the methane got there, you just need methane. And so there's two big games afoot in the world right now. There's a whole host of people that are doing what are called a carbon first approach, or excuse me, a hydrogen first approach, where they simply are creating as much hydrogen from this process as possible and not focusing on the carbon. And so the idea is that companies like Monolith and Hyrock, Monolith is a company in the US, been given $1 billion by the US government to build a plant in Nebraska of all places, and they're using a thermal plasma to ultimately do pyrolysis on methane and form solid carbon alongside hydrogen. Here in the UK, Hyrock is much the same kind of grand idea, also using thermal plasmas to do this. Making hydrogen, say vast quantities of hydrogen, and forms of solid carbon that are say like, very soot-like, kind of, they might say it's activated carbon, but there's still a long ways to go before one would kind of buy this as a product, let's say. And then there's other kind of emerging technologies, such as one out of University of California, Santa Barbara, and others, where they're basically doing the same thing. They're bubbling methane through molten salts. You get a solid carbon slag is the term in that field that you would kind of scrape off the top of that surface. Again, kind of a poorly graphitized material that comes off the surface. And then, the question is, what would you do with the carbon? It's obvious what one would do with the hydrogen. And then there's a group, and I count myself among them, that have been looking at let's focus on the carbon first and let that be the, if you will, the economic driver, at least the intellectual driver for making these processes. And then let's see if we can get the hydrogen for free and eventually scale that up. So the economic rationale, the kind of intellectual rationale is all built around the carbon, and the hydrogen just kind of comes for free in that case. And so that's predominantly what I'm going to talk about today, although I am doing some work in consortium with the other two processes. And so why would we focus on the carbon? Well, Mike Ashby, for those who don't know, famous engineer who became famous for plotting things very well in an intuitive way. And what's shown here on the y-axis of the right-hand plot is the scale of materials use, or in some cases it's oil and natural gas use in the world. And you can see that the only materials that come anywhere close to our human consumption and production is steel, concrete, and asphalt to natural gas. So if one wants to find a place to put carbon in the economy, those are the only three games in town. Everything else you're burying, right? Sure, you might shift supply demand a little bit, but you're not going to make a bunch of more activated carbon. So we, humanity, make somewhere around over 10 to the 6th metric tons, so millions of metric tons of carbon already, called activated carbon, that basically goes into tires, right? But very quickly, that we only need so many tires in the world, right? And so you can't just make a whole orders of magnitude more carbon and expect us to make orders of magnitude more tires or whatever the product might be, right? So the only places to put large quantities of carbon in the economy are to basically serve the purposes of steel, concrete, asphalt. We all know cement is a subcomponent of concrete. And so you're basically looking for one of those, and maybe early on, maybe some other high-value materials such as aluminum or copper might be good stores for that. And the reason one might do that from a climate change perspective is that those materials are responsible for a large fraction of our overall CO2 as a world, and certainly a large fraction of the manufacturing. So 30% of the manufacturing is the budget of the total CO2 emissions. And of that, you can see that cement and steel are about equal fifths of that. Yeah? So large motivation, both from the supply side and the demand side to do this. So we're not the only people that have thought of this. And however, what has been recently kind of a convergence of the world is the process that we've been running here at Cambridge for a long time is kind of the greatest hope for the process to do this. And so there's a number of kind of big recently funded initiatives that I'm a part of. Maybe the most relevant for us here in the UK is one funded by UKRI, where we're building a 5-ton per year demonstrator plant that needs to be online next year, and showing early demonstration of that. And then, the truth is that there's a large international body of private companies that are running this process that I'll talk about in their own labs and are already funding some of this work at, much larger values than this. Nonetheless, this is kind of what's in the public domain. I'm also part of a recently funded center called Hydrogen Production Center, which is NSF in the US, UKRI in the UK, the Australians and the Canadians as well, all around these types of ideas of methane pyrolysis, and then the Carbon Hub as well, doing much the same. Again, all basically interested in taking the carbon out of natural gas and then questions about what one does with it as one produces hydrogen. And so what's driving this now? Well, in the near term, what is really driving this is that is the massive growth in batteries. And so for those that don't know this, you might think, a lithium-ion battery is probably really engineered well to conduct electrons. That would be false, because what a lithium-ion battery is engineered well to do is to intercalate lithium ions. And actually the materials we choose for lithium-ion battery materials, particularly anodes and the cathodes, are pretty poor. Typically the cathode is a very poor conductor, especially when it doesn't have any lithium in it. And so almost all batteries in the world need somewhere on the order of 5% carbon added to them already. And most of that carbon comes in one of two forms, either carbon nanotubes, and so LG Chem is one of the world's largest producer of carbon nanotubes. All of that goes into batteries. And the other form is known as something called super P carbon, or people are exploring graphene as well, but these other forms of carbon. But what one really wants is some nice long-range conductivity that carbon nanotubes give, and that's what I'll talk about in this case. So batteries, and then what I'm showing next there is EMI shielding, are really driving the market today. And what's nice about those markets is that they're growing very quickly. And so it's relatively easy for an emerging technology to kind of feed an emerging sector. So one doesn't have to be at scale at day one. You can kind of grow with the industry. But frankly, that has no impact on climate other than the batteries that are produced to displace. It's not as if those are going to be large stores of carbon for us long term. One really needs to transition to automotive and aerospace in the more near-term future, and then long-term into structural materials. And that's where these carbons would ultimately need to displace steel, concrete, aluminium if one's going to make a big impact there. So as I said, batteries are the real need now. And what is interesting is this just kind of highlights what I'm talking about. In the cathode on the left here is where you can see all of that kind of interstitial space between the active material. The active material is kind of what looks like it's been cut away. That all that interstitial space is often filled with carbon to provide good electron conduction pathways to make it into kind of what the active material here is, where your electron has to meet with a lithium ion for those to then go into the material together. And so you need those two to meet at the same rate. Ideally, you have the electrons move a little bit faster than the lithium, so you're lithium limited. And so to do that, we're adding carbon now. So that's the driver now. And some companies are truly just doing that for lithium-ion battery purposes. And the South Koreans and LG Chem, so KIST up there in the top right, are really interested in that as its primary motivation. But you'll notice kind of a strange list of companies here that some would not consider very environmental, working on this, and then mixtures of very environmentally minded organizations here as well, all kind of running the process that I'll talk about today for largely more or less the same purposes. And what has really motivated this is the plot in the middle bottom here, which is that these material properties that I'll talk about today have doubled every 3 years for the last decade and a half or so. And so right now, humans' kind of strongest material that we make at scale is a military grade of carbon fiber. And so that's something I can't even buy, but it's a Japanese carbon fiber that goes into basically military fighter jets, kind of more or less. And just in the last year, the best nanotube-based carbon fiber is on par with that. So the best is 7 gigapascals of strength. The best carbon nanotube is 6.5 gigapascals of strength. So really within striking distance with a lot of headroom, right? It's still growing at a given rate. And this has ultimately interested a wide variety of different organizations. And already there's fair scale of some of these material production capabilities. So as I said, LG Chem is producing about 4 kilotons per year of carbon nanotube materials. Not quite from the same process that I'm going to spend most of my time talking about today, but nonetheless, it gives a sense of scale of where we could go. And they're adding a production plant at about 1 kiloton per year now, as well. So that's been their recent growth. And so what has led to this ultimate kind of improvement? It's fundamentally taking a material that is very disorganized, carbon nanotubes, and organizing them in a way where their properties are aligned with one another and they're kind of sharing the load, so to speak. And so I'll talk a lot about that, what that means. But basically what we get out of these materials is we get out of the reactor, and I'll spend more time talking about what these reactors look like. We get something that's kind of fairly isotropic, and you might think of isotropic as another way of saying disorganized, kind of equally dispersed in all directions. And these are bundles of nanotubes. And if we organize them and densify them, we basically move along the plot to the right, and that pushes our material properties up and to the right as well. And so, as I said, the best carbon fiber in the world is 7 gigapascals of strength, and recently published the best material property of the fibers that I'll talk about is 6.5 gigapascals. We had the world record taken from us last year. We were at 4.5 gigapascals of strength, but we're working to get it back. But nonetheless, that's the game that we're playing now as an international body, is pushing densifying these materials and aligning them better. So to tell you about the process as a whole, basically what it is a high temperature reaction where one has a gas phase process, so it's hydrogen coming in. So the background gas is hydrogen. And then you have iron, sulfur, and natural gas or biogas, again, a form of methane that isn't so important as long as it's methane. And ultimately what you get is you get catalysts that form free-floating in the gas phase, relatively high temperatures of this reactor, so 1200 degrees C. 1200 degrees C in hydrogen is not something to kind of take lightly, but nonetheless, many are running this. And then the nanotubes ultimately grow from the catalysts that form, the iron and the sulfur form a catalyst that grow the nanotubes. And the nanotubes, what fascinated me about this process is the nanotubes then self-assemble and make a macroscopic material that one just can pull out of the reactor. It looks like kind of a black candy floss, something you wouldn't want to feed your kids, but nonetheless is kind of this emergent property that we still can't fully explain mathematically, but it's fascinating to me nonetheless. And so this is what it looks like in one of our industrial colleagues that buys all the IP from Cambridge, and them processing these materials into fibers. And so what was shown there kind of initially was I'll do it again. This is the end of the reactor. This is the nanotubes coming out in a bulk form. Here are them coming onto a winder. And then basically after they come onto that winder, we've got lots of games we can play in terms of either stretching them and condensing them into a fiber, or we can flatten them out and turn them into a mat. That mat could be, conceivably infinitely long in one direction and basically just as wide as your roller is wide and coming out of the reactor, or you can do more traditional fiber processing techniques as well. And so that's fundamentally what we're studying. And why this process relative to the others? So there's three main ways one can make carbon nanotubes. And that is that one can make them on a flat substrate. And so, and that's kind of indicated by the yellowish color here. And that's still of great interest, but probably more for thin film applications, semiconductors, transistors, maybe ultimately sensing applications. We've got some work in that with Michael DeVolder, who's big in this area here at Cambridge. The way LG Chem makes these materials is they do a fluidized bed process. In fluidized bed, you basically have, rather than a flat substrate, you have balls, kind of relatively large substrates, large spherical substrates relative to the size of your catalyst, and then those grow nanotubes off the surface in a fluidized bed. And then there's the floating catalyst process. And what you'll notice is that the floating catalyst process, really stretches out here in an important indicator for us, which is a Raman signature, which is an indicator of, you can think of it as good to defective or graphitic to defective peaks here. And so what these materials are, they're extremely long nanotubes. So each individual nanotube might be hundreds of microns to a millimeter long. And that's far and away differentiated from these other processes that just don't grow that long of nanotubes, and certainly don't grow them at the same rate. So that is why there's interest in this process, particularly in that, everyone that I showed on that early plot are running this floating catalyst process rather than one of the others. And so, I've been working on this a while, kind of 15 years almost now. And what has emerged is not only kind of a scientific rationale around this, but some economic rationale. And there was a nice study done by Lang, who studied all of the catalytically driven industrial processes in the world. And when he kind of boiled them down to, are those that become viable have 4 characteristics that fall within certain ranges. And they really, if you think about them, have to do with either 2 expenses that an organization might have, and one is capital expenditure, and the other is operating expense. And so capital payback, i.e. you've bought a big plant and you need to pay it off, really scales then with reactor yield. So your payback period, the better your reactor yield, the faster you can pay back that plant, because you've bought a certain size of plant, i.e. a certain number of meters cubed, a certain volume, and you want to produce as much material per unit time in that reactor as possible. Also, you want to produce a good quality of that material, and so your catalyst, whether you're making nanotubes or ethanol or sustainable aviation fuels, whatever your catalytically driven process is the quality of that product will also affect your payback period. On the other side, the operating expenses is the refining cost scale with the product concentration. So if you have a very concentrated product, you don't have to refine it much further. If you have a very dilute product, you might have to spend a lot of energy refining it. We're particularly lucky in this case in that all our refining is simply taking a solid from the gas, and that's not very hard. So that's not a tough criteria for us. And then the other is a consumable cost, which is basically your number of products over your catalyst, and you might scale that by cost as well. And so in our case, at least now, the product value you might think is very high, and the catalyst is relatively cheap. It's just iron with a bit of sulfur, and you might even use iron oxide, rust, as your input here. And so this is those metrics now put on the ranges that that Lang found relative to the boxes, which are the not just our own groups, but the world's CNT processes being produced. So what I would argue is that the most important for us to improve is reactor yields, where we're just slightly over the minimum threshold, but not often, frankly. It's only kind of specialized conditions that we're running, and we're often trading one factor off to get there. Product concentration, we're close, and frankly, I don't think that's important because, again, our refining costs are cheap. We're pulling a solid out of a gas that doesn't cost us anything. Our product value to catalyst cost is really high because our catalysts are cheap relative to things like platinum and palladium, which other materials, other processes might run. But our biggest area of opportunity is improving catalyst selectivity. And to highlight that, we're less than 1% of our catalysts actually grow these materials. And so understanding that and why those catalysts aren't being used in as high rate as possible or a high fraction as possible is where we really could gain orders of magnitude improvement, and then that would directly improve our reactor yield. So that's where most of the academic interest is in this, and motivated by this industrial need. So to look at a little bit then at the catalysts themselves. So these are iron particles in the gas phase, an aerosol, running down a reactor. And so here's what a typical reactor looks like. It has a parabolic temperature profile. So if it's just a tube furnace, we are getting more sophisticated in the reactors, but this process is one that started basically in tube furnaces. And basically you come in cold, you get very hot in the middle of a tube furnace, and then as the gases leave, they cool down again. And what happens is your reactants break down initially, in particular your ferrocene and thiophene, that's your iron and your sulfur source. And when they break down, what's shown here in the heat map is on the y-axis is the diameter of the aerosol particle. So we're extracting these particles and making size distribution measurements along the axial location of the reactor here. So these are kind of plotted to scale here. And what you see is initially when the ferrocene, and particularly the thiophene, the sulfur breaks down, you get a burst of nucleation and those catalysts grow. But one of the interesting things is in our first kind of big finding in this field was that actually our catalysts go away. And that maybe is not so much of a surprise if you think about it, is that as a reactor gets hot, it can evaporate more material. And so basically these catalysts, the gas, you can think of it, has a greater capacity to store more gas phase iron particles or iron molecules, just like when you put sugar into your tea. If your tea is cold, you can't absorb much of the sugar, but if you heat it up, you can absorb all of your sugar. The same happens in a gas. And so we can absorb all of the molecules eventually, depending on the recipe, into the gas phase. And then what's interesting is what happens on the downstream is that as this temperature cools, you get a renucleation in the catalyst, and that's actually where all of your growth is. So your methane has gone through the high temperature region, and then you can think of this pyrolyzed methane, so these C radicals that then interact with a freshly nucleating catalyst set of particles, and that's when the real growth occurs. And so that was kind of our insight into how do we really optimize this process. So one thing that I showed you here is that this is a single pass. And the real dirty truth of this entire field is that everybody has been running hydrogen through on a once-through basis. And so we've actually been net consumers of hydrogen, not net producers, because we're not looping the process around. And so, nominally we're 90% hydrogen here, and if you're only passing hydrogen through once, you're not being very effective with your hydrogen. So a big result for us fairly recently in the last, say, year and a half has been we've shown that we can recycle ultimately these species and net produce hydrogen. So in other words, we can take the gas phase species that come out at the exit of the reactor, recycle them back in, and only put in new carbon and frankly much lower fraction of iron, and we can get substantially the same process to run. So that's what it looks like in a nice kind of diagram. This is what it looks like in a messy schematic here. But basically it's the same process where one is winding up the nanotubes, and then you bring the gas out, and then you ultimately feed that back around. We were doing some spectrometry as we do it just to look at what is in that gas, and then feeding it back in the front end. And then at the outlet of this, you also get clean hydrogen production. And so that we've now demonstrated. To kind of talk a little bit more about that, of course, the hydrogen's hydrogen, so you can simply just measure that as H2. What's interesting is do you get the same quality of carbon product? And what's interesting is you actually get an enhancement in carbon efficiency. So these are the efficiencies in our own lab scale reactors. And we get a substantial improvement in carbon efficiency. Again, you might not think that's much of a surprise because you're giving multiple passes through the reactor for that carbon to react. So you're giving it kind of more opportunity in that case. And then as we go to large-scale furnaces, we already know through our industrial collaborations that we get much higher carbon efficiency. So this is literally the number of carbon atoms that you put in the front end versus those that end up in carbon nanotube material at the back end is this metric here. And so we've got a lot of a room for improvement, and already we're doing pretty well on that industrially. And so also we can look at our methane input, and we can see that we need much less methane input, ultimately with recycling as well. So it's a benefit in both of those. And largely we get the same overall production rate, so very similar. So this is normalized to our kind of baseline production rate, but we get substantially better run time. So our reactors run for longer without clogging, and we get, as I said, much higher carbon conversion efficiency. So this is the process running in our own labs. These are the nanotubes coming out of the bottom of a reactor, kind of running from right to left on your screen there. So, so to kind of sum up at least what we understand intellectually and from a scientific basis, we understand the inlet dynamics pretty well, and they're not that important, I would argue. Is that basically these precursors break down, they form catalysts in a way that we, humanity, know how to run equations on, and then the process moves to the middle, and in the middle of the reactor, you're at high temperatures, and ultimately you're not so much kinetically limited, but you're just thermodynamically limited. So if one just looks at, what would these materials like to go to at these temperatures, given time to infinity, you come out pretty close with the same answer here. So you can run Gibbs free energy minimization, if you know what that is, and you get the right result. But where the real interest is that in this downstream process, we're really kinetically controlled, and we, humanity, don't know those kinetics very well. And that's where our real interest is, primarily because that's where we get the majority of our nanotube formation. So not only is it an area of academic interest, it's also the primary interest of what we'd want to do from an industrial production point of view. So we have lots of interesting dynamics and physics going on here. We have concentrations, gradients across a reactor. So this is meant to be a cylindrical reactor representation here, where we have, say, temperature varying in the radial direction, the particle concentration varying. We might have interesting aerosol. We certainly have interesting aerosol dynamics, so nucleation, clustering, growth, phoretic forces, like as a result of temperature gradients. We have this emerging solid material that is forming from what wasn't intercalated material. And we aren't yet describing that well mathematically in our processes. All of that is really interesting. I would say what is not interesting is the fluid dynamics. The fluid dynamics are basically very low Reynolds number flow. So it's laminar flow, you know, the kind of thing we've known about in humanity for a long time, and we can describe that very well. And so in some cases, we will be better at making models and further on our understanding of these processes, and I'll talk about some of those models. In other cases, we're going to be better at making measurements. And so classically, we humans are really poor at nucleation. You might think that has been studied a fair amount because rain is basically a nucleation process where water droplets condense on species in the upper atmosphere. And you'd think we've gotten good at that. We are still orders of magnitude off from theory and measurement in being able to explain when, for example, a water droplet will form around a soot particle as it's emitted from a gas turbine engine. And that has a huge impact to contrails, which are really hot in the news right now. They're roughly, for those that don't know, that roughly half of the climate change impact of a flight is due to the contrails alone. And yet, we are about a factor of 1,000 off in explaining with an equation when a particle will form a water droplet and when we won't. We're no better here, so I don't give us much chance at being able to model this well. I think we're going to have to measure it to get close. So in that case, we're going to be looking at the nucleation and growth rate of some of these species by a measurement. In some cases, frankly, I trust our ability to model better than we can go in and make measurements in some cases. So I'll talk a little bit about both of those. When we look at the process as a whole, again, kind of at a very macro level, and everyone who's published on this, and there's kind of 25 different research, maybe 50 now research groups throughout the world that are actively working in this process, and we put them all of their recipes for those that report them onto a logarithmic scale, and one should always be suspicious of logarithmic scales, but nonetheless it does provide some guidance here to us, is that we get pretty close clustering in the recipes in terms of carbon and iron that everyone feeds into this process. And so, that is somehow fundamentally telling us that either A, people are just really influenced by the recipes others have done, which might be the case, but it probably is that there's enough motivation to study this now by enough different groups that we're not able to kind of go far outside of these ranges, and the question is why? And does that tell us something about the process by which we could then enhance the process? And so one thing that we, humanity, can do pretty well is we can describe soot formation well, and soot is kind of the enemy here. If what we want to produce is really nice ordered carbons, you might imagine that as we increase the carbon content, we are more likely to form soot, and that would be a bad thing for us, right? So we humanity have gotten pretty good at describing soot formation through equations that I won't bore you through at 6 p.m. at night, but nonetheless we can do that. We can also describe iron nucleation and growth very well, and so we've got some of the tools at our disposal to be able to do this, and just to kind of represent that is that the X's here are our measurement data where we're sucking the products out of at various points along the axis, so the distance down the reactor, and we can suck out and we can see, for example, how much acetylene and ethene are being produced relative to the models. And there's a variety of different models, but by and large, this is a linear scale, not a logarithmic scale. I'm really happy with the agreement here. So we're not far off in terms of being able to describe the carbon chemistry well. But where we are really bad is describing ultimately some of the carbon nanotube growth rates. And so if I take that same plot that was 3 before, is a iron and carbon axis, and I start to look at, okay, what limits us on, again, an iron on the y-axis, carbon on the x-axis. And what happens is that as we start putting in lots of iron, the iron particles basically collide together too much and grow too big. So we need these particles to be nanoparticles. If they get to be too largish of nanoparticles or even micron-sized particles, they don't grow nanotubes anymore. On the other end, if we just put in too much carbon, we get soot production pathways. And that's not desirable either. And what happens if we go up and to the right, where we kind of put commensurate amounts of carbon and iron in, we ultimately enter a regime where we're kinetically limited, where basically two acetylene molecules start to find themselves collide with one another slightly faster than what we would like, which is an acetylene molecule colliding with an iron particle. And that collision to a first order is the dominant reaction pathway in this system. So we can measure collision dynamics. And so and one way we do that is, this is kind of harkens back to what our group has spent some time developing, is a number of different measurement principles. So kind of particle measurement 101 is that often we have non-spherical particles. This is kind of soot-like, but it could be a nanotube too. And it's not a sphere, but yet we have all these ways of measuring things that would be a sphere that would have the same properties. And so one thing you could do is you could say, well, if I put this non-spherical object into an electric field and I moved it across a gas, and some might know that term as mobility, you could ask what sphere would move across the gas in the same way under the same electric field. That would tell you something about that. And when you compare that sphere to a sphere that says, well, what if we ultimately shrunk all of that mass down into one spherical ball? What would that ultimately result in? It would give you a different sphere of the same density. And then you might ask the question of, if you were to jump out of a plane and you were to have a drag force against you and gravity forcing you down, what sphere would have the same terminal velocity as you jumping out of a plane, right? So a particle here, a non-spherical particle, has a terminal velocity as well, and we can measure that spherical diameter as well. So with a variety of these, we can't necessarily put every point of the primary particle onto the larger particle, but we can ultimately determine what's known as the fractal dimension of these materials, and that's incredibly useful for some of these measurements. And then, as I said, we can also look at what are organics versus solids on this as well by either running them through a catalyst or not. So we've got a variety of tools at our disposal here. And we can start to look at things like soot production. And again, soot production in this process is the enemy, but yet it is kind of where we want to go. It is, when we get good at this, we will balance being very high carbon concentrations, in other words, high inputs of methane, without producing soot. That's really the goal, to get these reactors to be more dense. And what one sees is that as you input more methane, you get an increasing amount of acetylene up to a point. And eventually, what happens is, as you start increasing methane and increasing temperature, you ultimately max out on the amount of acetylene that's in the reactor, because the acetylene starts to get consumed and produced into soot. So everything that would kind of be up in this region starts to be soot production. And so we can measure that in another way, of course, as well, is that we can put in different amounts of methane, and we can start to increase the temperature and see when soot production starts to come. So this is kind of like what one does in an automotive emissions test in Europe when we're doing type approval testing, is that you're measuring particle counts coming out of the reactor, where we're not putting in iron catalyst now. And you just see, when this is logarithmic here, when do you start getting orders of magnitude more particles coming out than initially? And that tells you when you start to get soot production. And then we can do size distributions, and you can kind of look at what is the amount of mass that then is consumed in the unwanted species soot relative to the thing that you do want. So that's about what you don't want. Now let's talk about what we do want in this process. We'd like to have ordered materials, carbon nanotubes that grow and are ordered. And to order them better, we need to understand what is the process of this kind of natural self-assembly that they're doing in the gas phase. And that has been intellectually my most kind of motivating factor in all of this, because other aerosol processes don't do this. Spheres don't do this, and I'll tell you why in a minute. And so we'd like to understand that. And the other thing we'd like to understand is catalyst coarsening, and we'd like to be able to prevent that. And we'd like to prevent that because we could get more catalyst to grow nanotubes if we prevent this process. And we've got, as I said, orders of magnitude improvement to make here. So on the first one, we can take some motivation. This is, again, another reactor running in our lab. We've got half a dozen of these things running. The nanotubes coming out, it's a slower process here where we're studying it a little more. And what we're looking for is this emergent properties. And you can think that polymer science kind of did this a few decades ago, right? So polymer physicists were looking at these types of processes where you get monomers ultimately polymerizing and then assembling into materials. And we can think of analogous processes in the gas phase. And so the first thing we have collisions between nanotubes, and that's Brownian motion walking these materials around. They collide with one another, and they have an incredible amount of surface energy. And that surface energy, if given the chance, wants to be lowered, right? So they would prefer to be in bundles if they had their kind of energetic preference allowed. But what happens is they bundle up to a point, and then you start getting cluster formation. And so what happens is that this bundling occurs up to a point, but eventually the structures can't collapse and minimize energy anymore. And it's once cluster formation goes that you ultimately can go through one of two different pathways that we're not fully convinced of which is the dominant pathway yet. You either get a process called cluster-cluster aggregation, or a gelation that occurs straight from the individual cluster growing larger and larger. And that's what we're spending our time investigating. And to do that, we needed to know what are the rates of rod-like objects colliding with one another. So Einstein, a long time ago, worked out what is the rate at which spherical objects would collide with one another undergoing Brownian motion. No one had yet asked the question, what do long 1D objects do? And so we simulated it. It took kind of advanced computers to do that, but you basically put one object in a simulation domain, you walk the other one around with Brownian motion, you do that a few million times, and you get some trends out that one can collapse. And what's nice, what's shown on the left, is that if we use good non-dimensional analysis, we can collapse this down into equations that we can describe this well. But maybe what's important here is this on the right-hand side is this beta. So beta is I didn't talk about it. Beta is the collision kernel. So the rate of this whole process is basically this unknown parameter beta here times the concentration of one species colliding with the concentration of another species. So this beta is the thing we don't know, and that's what we need to put in our equations. And what's interesting about beta for rods is that it's orders of magnitude, or an order of magnitude larger than than spheres are. So what's shown in these dotted lines here are spheres of either the same mass. In other words, you can think of a nanotube being collapsed down into the same mass at the same density, or a sphere that is as large as the nanotube is long, right? And either one of those is an order of magnitude lower collision rates than the nanotubes. And that's why we don't see self-assembly of particles in a flame, let's say, right? We produce lots of soot in flames. And carbon black production is like optimized for soot production or carbon production. We don't see self-assembly in that way, but yet these nanotubes we do, and this is fundamentally the reason why. And so our emerging understanding of this process is that you get individual nanotubes that collide together. The rate at which they form these bundles, at least initially, is extremely fast relative to their collision rates, even though their collision rates are fast. But what we know is that that must slow, because eventually we get a material out that looks like this, where we get lots of bundles, of say 10 nanotubes roughly in a bundle, forming a macroscopic material. And so we can simulate this. We've been working on this a while, of taking nanotubes into a simulation domain. We can simulate kind of every atom, but frankly, we run out of computational power very quickly when one goes to hundreds of microns or millimeters long. So we have to be a bit smarter in the algorithms we're putting in. So we parameterize bead spring models with atomistic models, and you're able to describe this. And what's interesting is that we get a process where we think of it as kind of the reorientation or the coalescence. If it was two water droplets coming together, you would think of those water droplets coalescing into a sphere. This is kind of the analogous processes of two rods coalescing into a single rod. And that rate, depending on the collision angle, varies a bit. And it's on the orders of tens of nanoseconds. But as the nanotubes grow in length, that process, that time scale, ultimately increases and starts to approach that of the collision time. So, very low time scales here would be very fast processes, very long time scales are slow processes. And while the collisions are faster than spheres, they're still orders of magnitude slower than ultimately the nanotubes. And so as we've kind of gotten better at doing some of these modelings, what we're finding is that we start to see for long nanotubes, length here on the x-axis, time scales that start to approach the collision time scale, and that's where you get your emergent three-dimensional material forming. And so we've done a lot of work on that fairly recently and looked at these nucleation points where you get a macroscopic object forming out of these nanoscopic components. So that's kind of to understand that. I'm going to come back to that here in a minute. The other thing that we want to understand better is the catalyst coarsening. So these are the things that grow the nanotubes. And what nature, I'm going to kind of jump right here. What nature will give you is Brownian dynamics. There's a solution to this equation where basically it says any aerosol, this could be raindrops in the air, it could be COVID coming out of our mouths, any of those that are high enough density and they're undergoing Brownian collision with one another, nature will always pull that to a log normal distribution that has a given geometric standard deviation. Right? And for those that don't think like in log space, you can think of it as a normal distribution, a bell curve that has a standard deviation just on a logarithmic scale. Yeah? And it doesn't matter how complex the structure initially. So, that might kind of induce things in your mind like entropy that is kind of forming here, and we're losing information about what the initial structure was. And all processes basically go to this. And we need to fight this, basically. This is the enemy, in that it creates a very broad distribution of catalyst sizes. And we ideally would like to have the right size growing our nanotubes, and this is what we need to combat against. And so one way to do that is to suppress the collision rate between various particles. And so if one brings charges into a system, i.e. plasmas often have lots of charges around, and if we can control those charges to predominantly one polarity of those charges to attach to particles, you can get dramatically lower geometric standard deviation. So this is kind of what nature is bringing you to, and this is where we've been able to get some work recently and then grow nanotubes from these materials. It gets very mathy, but let's just say that one can produce relatively monodisperse particles when you introduce charge into the process, and we can do that experimentally as well as in our equations and ultimately describe that. So this geometric standard deviation, GSD, is what we're trying to ultimately get to be a relatively low number. A perfect delta function would be a geometric standard deviation of 1. 1.1 would be fantastic, just to, probably unachievable. 1.2 is very good for us. So we're excited about that, now being able to bring that into the reactor. The other way we could do it is we could simply size select catalysts. So all these techniques that I told you about how one measures particles, those can be used as size selectors. reactors as well. So you can put a particle in an electric field and only let a certain fraction of those through, and those could have extremely narrow size distributions. And I mean narrow at the angstrom level, so 4.3 nanometers exactly. And you can bring that into a reactor, and that is very useful. It allows you to grow fantastic nanotubes. The problem is you're throwing away everything else. So by size selecting, it means that kind of the dirty thing is that you're moving a lot of it under the carpet, so to speak. But if one does that, you can kind of do some fantastic things. So one of the holy grails in carbon nanotube synthesis for a long time has been to grow a very precise form of nanotube where one is controlling the chiral angle. So if you think of the chiral angle as you have a sheet of graphene and you can roll that graphene up in any direction, humanity would like to roll that up in a very specific angle, and it would give you very known properties that would be good. And so if you start to control catalysts in this way, you can do that. Do I ever think we can do that in a mass production scale? No. But maybe for thin film applications we could. And so there's some motivation kind of in other industries for that. Another thing that is of course interesting is to control this emergent behavior. And so what others had shown at Rice University is that in colloids with carbon nanotubes, one could apply electric fields or electromagnetic fields, Tesla coils, and you could get a net orientation of the materials. And we thought, great. Very easy for them to do at room temperature in water. Let's see if we can do this at 1200 degrees C in hydrogen. And it turns out it does work. The one thing that we didn't know going into this is what would be the type of field that one needs. And so it turns out that one needs an alternating field rather than a DC field, because what one first needs before you can orient anything is that you need to have the nanotubes be stiff. And so if you have electrons moving back and forth in an alternating field, you get by Maxwell's equation, you get a magnetic field that goes around that, and that serves to stiffen the nanotube. And once it's stiff, you can imagine you can align dried spaghetti. You can't align wet spaghetti, right? And so you need to dry the spaghetti, so to speak, first to be able to then align it in a useful way. And when you do that, it works really well. So this is another result that we're really excited about is we get some, you can think of this y-axis as an orientation parameter, think of it as kind of the degree of alignment here, and we get that going up and to the right substantially as we increase our field intensity there. But that's not the whole story. If we've got a long way to go in this, and I would say a lot of games to play. So if we look at what the polymer community did to get carbon fibers, they basically from the late 60s to the early 70s, they got better and better at drawing these materials out, and as they drew them out, they aligned them better and better. And you can see that they're at draw ratios of over 100, and that gets you to these commercial scale carbon fibers and the very high-end military grade fibers that I talked about right at the beginning. We're only in the infancy there, and so we're getting substantially high strengths and modulus, but yet we're nowhere near the draw ratio. So I have a lot of hope that with better techniques to draw these materials out, we will achieve better and better material properties there. So the way we, as a community, have been doing this, and this is work from our lab, is that you put these materials into very strong acids. Those acids give protons to the surface. Those protons repel the nanotubes and overcome the surface energy. And then if you can do that, then you can substantially align these materials. And that's how we go from materials that initially look like this, fibers that look like this, to fibers that look like this and become very dense. And so that game is being played as well. It's kind of an outside of the reactor thing, but we're playing that game. And our best material to date is this one. This is the 4.5 gigapascal strength one, where I'm comparing it to every other high-end material that we, humanity, produce. And what you can see is that we get pretty good overall material properties here. So we're not the best in any one yet, but we're near the best in all categories, and we've got a lot of room for improvement. So to give you the sense, an individual nanotube has a strength of 100 gigapascals, and we're at 4.5 to 6.5 right now. So there's a lot of headroom in this space. So I'll end with maybe 3 takeaways for sustainable carbons. I think for this to really be viable, where the climate cares, not just that industry cares, we need to get reactor yields up, and they need to be substantially higher than where they're at now. About a factor of 10 would probably put us in good stead, and ultimately with the goal of getting them up by a factor of 100. Our catalyst efficiency, I think the way to do that is by improving catalyst efficiency and getting better at making catalysts and keeping them from agglomerating with them will be ways in which that process is largely achieved. And then I think ultimately our aerogel, the macroscopic assembly of these materials will need to be controlled in a way, and so electric fields are likely a way to do that in situ, just like the carbon fiber industry went and aligned material production at every stage of the overall process. We're going to have to do the same here to get high-end properties. And I think even with that, post-treatment processes will still be necessary to get the high-end properties. Now maybe lots of, I mean, we're not order of magnitude, but we're substantially stronger than steel is, and so maybe there's lots of applications where you don't need to actually play some of these games once you get good at the others. So I still think stretching for alignment will be a game that we continue to play, and ultimately we need better contribution of all of the materials kind of within, so all of the nanotubes need to kind of share the load, so to speak. So with that, I will thank, of course, I do very little of this work, as you all know. It's a team of researchers in the lab that really spend their time working on these, so all the thanks goes to them. With that, I'd be happy to take any questions.